So today we want to go a little deeper into independent and dependent events. And so in the last lesson, right, we learned the following two rules. And so you can see here, if events A and B are independent, right, they are independent, then the probability of A times the probability of the probability of A and B is equivalent to the probability of A times the probability of B. So that's if they're independent of each other. And then we also learned this is called the complement rule here. They didn't label it that, did they? I'll write it right here. So here, I'm going to move this. And the complement rule basically states that the probability of not A occurring is equivalent to 1 minus the probability of A occurring. And so that's actually really important as we walk through this lesson. So keep those in mind. So we're going to practice applying these situations that are more complicated. Number one. Okay, so guessing. A multiple choice quiz has 3 questions, each with 5 answer choices. Okay, so you can see here, right? This is question 1 right here. And you can see that it has, A, B, C, D, or E, right? And so you have no idea what the answer is to any question and have to guess each answer. Okay, so this actually is going to be important as we walk through this. So keep this in mind. And just to make things just a little simpler as we walk through here, I'm going to let a capital A be equal to answering a question correctly. So A, find the probability of answering the first question correctly. So I'm going to do it this way where I'm going to write, okay, let's find the probability of, and then A represents answering the question correctly. And sometimes what we'll do is we'll put a little subscript following it just to say, oh, it just refers to question 1. Okay. So I'm just going to do this here since it's the first time I'm showing this. So there's that. So it's kind of like just adding like a first name to someone's last name. So instead of calling me Lavis, you might call me Doug Lavis, right? Just gives a little name to A. So we'll say refers to the first question. So it refers to question 1. Okay, and we are doing just theoretical probability here. So what, how many questions, how many choices do you have for question 1 that you could choose? 5, right? Remember, for question 1, you have 5 choices. Okay, A, B, C, D, or E. So of those 5 choices, right, how many of them are favorable? Only 1, right? Only 1 will be the correct answer, 1 out of the 5. And when you put that on your calculator, right, 1 divided by 5 is 0.2, right? Okay, or it's 20%. Let's see here. Are we okay with that one? Let's take a look at the next one. Find the probability of answering the first two questions correctly. So I want to find the probability of A1 and A2. I'll bump this over. Okay, well, if those are independent events, then we can calculate it, right? We have a method of doing that. And notice, are A1 and A2 going to be independent of each other? What you answer for one, is that going to be dependent on when you answer question number two? Like, are they going to depend on each other? No, and I'm seeing people shake their heads. No, and it's because it doesn't matter, right? They can be the same answer, they could be different answers, right? We don't know. So A1 and A2, okay, are independent. Okay, so we know from up above, right, that if they're independent, that you could just multiply then the probability of A and the probability of B. So I'm going to come down here and rewrite this to be the probability of A1 occurring times the probability of A2 occurring. Did we already figure out what the probability of A1 is? Right over here. So I could just put that here, right? Is A2, the probability of A2 going to be any different? Okay, so for A1, we know it's going to be 1 in 5, right? Probability of A2, isn't it also have 5 choices and only one of them will be correct? So it's also 1 in 5. So when I multiply those, I get 1 in 25, which is 0.04 or 4 hundredths, which is the answer, right? We like our answers in decimal with this curriculum. Okay, or we could say 4%. Are we okay with that one? Yeah? Okay. Find the probability of answering the first question incorrectly. Find the probability of answering the first question incorrectly. So, um, isn't that the same as not A1? Do you agree? And remember, if it's not A1, it's the same as 1 minus the probability of A1. And again, we calculated the probability of A1 up here, didn't we? So can't I just put that down here? So this is going to be 1 minus the 1/5. 1 minus 1/5, isn't that 4/5? Which as a decimal is 0.8. Right, or it's 80%, right? D, find the probability of answering all 3 questions correctly. So this is the probability, right, of A1, okay, and A2 and A3, right? So all three questions correctly. So remember, the events answering question 1, answering question 2, answering question 3 are independent events. So that means I can rewrite this to be the probability of A1 times the probability of A2 times the probability of A3, which we know, right? We already found out, right, in part A, right? We know that it's 1 in 5 for question 1, right? And then we also know it's 1 in 5 for question 2, right? So there's one answer correct out of the 5 choices. And then for question 2, there's one correct answer out of the 5 choices. And for question 3, there's one correct answer out of the 5 choices. So this gives me 1 in 125, which when you put that on your calculator is 0.008. So, or that's a 0.8% chance that you can guess and get all 3 questions correct. Right? That's if you haven't studied at all, have no clue what the answers are, then you have a 0.8% chance of guessing correctly on all 3 questions. Are we okay with that? Okay. Okay, and then E. It says find the probability of answering none of the questions correctly. Well, I'm going to start way over here to write this. So the probability of none correct is going to be equal to the probability of, running out of room, aren't I? I'll write it this way, not A1 and not A2 and not A3. Isn't that right? They're independent events, so isn't this the same as the probability of not A1 times the probability of not A2 times the probability of not A3? Wait, didn't we already find not A1, not A2, right? Wasn't this not A1 up here? So I'm going to take this 4/5 that's here, okay, and I'm going to stick that into these ones here. So this, right, they're all not, right? So this is equal to 4/5 times 4/5 times 4/5. Which, isn't that 64 over 125? So I'm going to stick that on my calculator, and I'm going to get 0.512. Right? Or 51.2%, right? Chance. that you'll get all 3 questions wrong. How are we doing with that? Okay, so let's come over here. This last one, it says find the probability of answering at least one of the questions correctly. Uh-oh. So I'm going to find here the probability of at least one. Correct. Well, the probability of at least one, right? That means of the 3 questions, you get 1 correct, or you get 2 correct, or you get all 3 correct, right? Which situation is it leaving out if you have at least 1 correct? Huh? Getting what? Getting the other 2 wrong? Okay. Well, okay, so of the 3 questions, right, for it to be the probability of at least 1, right? That means that, so I'm holding up 3 fingers, right? So if I have all 3 fingers correct, right, that's at least 1, right? If I get 2, so I'm holding up 2 of the fingers. If I have 2 of my questions correct, is that still at least 1? So you have to figure out all the different probabilities of 2 of them, right? And then if I have 1 correct, does that also, right? So what is the only scenario that's left out here? Huh? Getting none correct, right? You see that? So finding at least 1 correct is the same as finding 1 minus the probability that, I'll say, not at least 1. But here's the thing. It's the probability that none are correct. So when you see the wording at least 1, it's the same as 1 minus the probability of none. Because at least 1, then you have to find all the different probabilities that it can be. Okay, so we want to memorize this. Or you could just find, well, what is the probability of none correct? And if you subtract that for 1, that should encompass all the other scenarios. So notice in this case, right, it would be 1 minus. Didn't we already figure out that you didn't get all 3 correct as one of our problems? Didn't we already calculate this, the probability of none? Over here? Bless you. Right? We already calculated it over here. So I'm going to take that value and I'm going to put that in. So it's going to be 1 minus, and then it's 0.512. Okay, and when you subtract those, you're going to get 0.488. So the probability of at least 1 being correct, you have basically a 48.8% chance. So, okay. So does that probability of at least 1 make sense to you? So anytime in a problem, you're going to say, well, what's the probability that at least 1, right? Anytime you see that, you're going to go, oh, it's 1 minus the probability of none. Okay, and it's usually easier to calculate the probability of none because it's one scenario. Okay, can we move on? Okay, let's come here. Problem 2, call center. Okay, when a call center received an airline, when a call is received at an airline's call center, the probability that it comes from abroad is 0.32, right? 32 hundredths, or right, 32%. Okay, and the probability that it is to make a change to an existing reservation is 0.38. Suppose you are told that the calls are independent. Okay, so the calls are independent of each other. So as they come in, right, the call that happens before is not, the call that happens isn't dependent on anything that's come before it or anything that will come after it. So let's do this because I think this will be easy for us. So I'm going to let A be equal to that the call is from abroad. And I'm going to let B be equal to calling to change, right? An existing reservation. And we actually know in the problem, they tell you that the probability of A is the 0.32, right? Because that is what it's highlighted in the orange, right? And then highlighted in the green, it tells me the probability of B to change it is 0.38. Are we okay with that? So what is the probability that 3 calls in a row are about changing an existing reservation? Okay. I meant to use C for change instead of B. Are you guys okay if I switch that to the B to a C here? Sorry. That'll help me keep straight, right? Abroad and change, A and C. So what's the probability that the 3 calls in a row are changing an existing reservation? So we're trying to find here the probability that the first call is a change, and the second call is a change, and the third call is a change. So if they're independent events, don't you just need to multiply them? Remember it said that at the beginning, the last sentence, right? Are independent. So it means I get to just multiply those probabilities. And so we know that the probability of a change is what's highlighted in green. And so it's the 0.38. So it's 0.38 times 0.38 times 0.38, which is 0.38 cubed. When I cube that, I get 0.055. or it's a 5.5% chance, right? For part B, notice here it says, what is the probability that there are 5 calls received and only the 5th call is from abroad? Well, we have to know what's the probability then of it not being abroad, right? In order to do this. And I think as we go through this, you'll understand. So first, I need the probability of not A, which is 1 minus the probability of A. So that's going to be 1 minus, and then the call from abroad, isn't that what I've highlighted in orange, the 0.32? So it's going to be 0.68. Okay, so now says that what is the probability that the 5th call received is the only one that's from abroad? So notice here, I'm going to as far over as I can make it. So I want the probability of not A1, right? The first call is not from abroad, and the second call is not from abroad, and the third call is not from abroad, and the fourth call is not from abroad. Okay, and the fifth call is from abroad. You see that? So that's why I had to figure out, well, what is the not A1? Because I need it for these 4, don't I? So that means that this is going to be the probability that since they're independent events, then I need the probability of not A1, and I need to multiply that by the probability of not A2 times the probability of not A3 times the probability of not A4 times the probability of A5. So I'm going to take that probability, right, of not not A, and I'm going to stick that into all of these locations. So it's going to be that 0.68 times 0.68 times 0.68 times 0.68. And then what is the last one going to be? What's the probability of A occurring? Isn't that the 0.32? So this is going to be 0.68, and there's 4 of them, to the 4th power times the 0.32. And now I have to stick that on my calculator, right? And when you do that, you'll get 0.068. So that's basically, you have a 6.8 chance that the first 4 calls are not from abroad, and the last one is. Are we okay with that? Yeah. Give a few people a minute to finish copying that. C. Okay, C. Now C is going to be a little bit more complicated. Can I move this up? Looks like it. Okay. So now for C, I just know I need a lot of space for C. So let's just do this. I think that will be enough space for D. D doesn't take as much space. But C, I'm going to need quite a bit of space. C says, if there are 4 calls received, what is the probability that at least one of them is to make a change to an existing reservation? Uh-oh, did you see that? At least one is right there. So that's one of those problems. Okay, so let's just say here, I'm going to write it way over here because I know. So the probability, at least one change in 4. So we know that that's the same as 1 minus the probability of not at least one change in 4. Now I'm not going to keep writing the not because I think that we'll just get to where we don't need to. So not at least one change in 4 because we just need to get to the point where we just know it's 1 minus the probability of none. Okay, so I'm going to leave some space. I'm going to come down here. Bless you. I'm going to find the probability of none down here. Let's see here. So the probability of none, that means that I'm going to have here the probability, so it's none change, right? So the probability of a change, right? Not, so this is going to be not C1, okay, and not C2, and not C3, and there's 4 phone calls, so I'll do not C4. So isn't this going to be the same as the probability of not C1? They're independent events, so times the probability of not C2 times the probability of not C3 times the probability of not C4. Uh-oh. So what do I need here? I don't know what the probability of not C is, do I? Okay, fine. So that means now I'm going to come over here. And I'm going to find, okay, fine. What's the probability of not C? Well, isn't the probability of not C the same as 1 minus the probability of C, right, of a change? And we know that a change is the 0.38 that was all the way at the beginning, right, way up here. Sorry, I made a mistake here. I'm fixing it. Okay. You're right. This was in the original problem. They told me the probability of C was 0.38. So I'm going to come down here and figure out what not C is. 1 minus 0.38, which is equal to 0.62. So I'm going to take that value right here. Right, and I'm going to stick it into these 4 locations here, right? Okay, so that's that 0.62. So it's going to be 0.62 times 0.62 times 0.62 times 0.62. And that's 0.62 to the 4th power, because it's usually easier just to do that on the calculator, raise it to the 4th power, than typing that in a million times. And when I put that on my calculator, I'm going to get 0.148. Now, was that the correct answer? No, if you remember correctly, we needed the probability that none of the phone calls were for a change. Okay, up here. And so now we've got to take and stick this value back up into that location. So let me highlight this. Okay, and that's going to go in this location here is what I'm going to do. So I know it's the 0.148. So this is equal to 1 minus that 0.0148, which gives me 0.852. And that's actually the answer to this problem. I'll highlight it in yellow, right? Or we could say that that is 85.2% chance, right? That at least one of the 4 phone calls will be to change an existing reservation. So most of the time, right, they can expect to get a change to an existing reservation. Okay, how are we doing? Oh, okay. D, if there are 6 calls received, what's the probability that only the 3rd call is about changing an existing reservation? 6 calls, oh my gosh. I think they're trying to kill me. Were you done copying that down? Is anyone still copying this down? Okay, so D, so 6 calls, and the 3rd call is the only one about changing. All the others were not changing. So we're looking for the probability, right, of not C1, right, and not C2, and, oh, C3 is a change, right, call 3. Okay, and then call 4, 5, and 6 are not changes. Okay. And if they're all independent, then this would be the probability of not C1 times the probability of not C2 times the probability of C3 times the probability of not C4 times the probability of not C5 times the probability of not C6. Well, notice here there's 1, 2, 3, 4, there's 5 not C's. So we have here the probability, right, of not C, and we'll raise that to the 5th power, times the probability of C3. Well, didn't we already figure out the probability of a not C down below? Oh. That was the 0.62. And then we know from up above that the probability of C3 is the 0.38. And when I multiply those on my calculator, I get 0.35. Right? Or that's a 35% chance, right? That the third call will be about changing a reservation while the other 5 will not. Okay, how are we doing there? Are we good with that one? Okay. Let's go to the next exploration. It says here multiplication rule with dependent events. So now if they are dependent on each other, then what do we do? So if two events are dependent, we need to modify the rule slightly. And you can see here, well, let's do this. If I want to have, I'm just going to draw a small, small rectangle here. It doesn't have to be huge. And then I'll draw a second one here. And let's make the first one for independent events. And make the second one for dependent events. So this is one event, event A. This one here is event B. Okay, and notice here there's no overlap, right, for the two events. But for dependent events, notice that there is overlap. Huh. For these two events, right, where this is A and this is event B. So if I want to find the probability of A and B occurring for dependent events, right, these are going to be dependent events, notice that my formula changes just slightly here. It's the probability of A times the probability of B given A. Okay. So, and what this does here is it allows for the overlap to not be counted twice. So it says here, we will most commonly use the version of this rule when we are sampling without replacement. This is a big deal here. So without replacement, meaning you're not putting something back. So like in the example below. So I'm going to teach this by doing the example. It says here, light bulbs. 12 light bulbs are tested to see if they last as long as the manufacturer claims they do. 3 light bulbs fail the test. The rest pass. Suppose 2 light bulbs are selected at random without replacement. So I'm going to let A be equal to the bulb fails. And I'm going to let B be equal to the bulb passes. Find the probability that both bulbs failed the test. So I want to find the probability of A1 occurring and A2 occurring. Okay. But notice, right, A2, doesn't this depend on what gets pulled the first time? Think about it, right? If you pull a bulb that fails the first time, you have fewer bulbs that will be failing the second time to choose from. Okay, so this depends on pulling A1. So when I go to write this, this will be the same then as the probability of A1 times the probability of A2 given A1 occurred. I like to think of it this way. So let's, for the first one, A1 occurring, right? We're looking for the probability that it fails. So how many of the bulbs fail? Oh, wait, hang on. Let's make sure we have information here. How many bulbs are there total? Don't we have 12 bulbs? Do you see that? So we have 12 bulbs. How many of them will fail? Isn't it 3? And if you subtract those, doesn't that tell me that 9 will pass? You see that? Okay, so for the first bulb, how many bulbs do we have to choose from total? For the first bulb, how many bulbs total are there, you guys? 12. Okay, and we're looking for the favorable is that the bulb actually fails, right? So how many of the bulbs will fail? 3. Okay, times. Are you okay with that? Notice now for the second one, how many bulbs do we have to choose from given that we've already chosen one bulb? Well, if we had 12 bulbs and we take one out, how many bulbs do we have left? So we have 11 bulbs to choose from now for the second one. Because it depends on what happens the first time, right? So, and we're looking for the second bulb to also fail. Well, they only have 3 bulbs to fail. If we pick the first one to be a bulb that fails, what's the probability that the second bulb will fail? Well, there's only 2 more bulbs left that could fail, right? According to how they defined it. Does that make sense? Okay, so 3 times 2 is 6. 12 times 11 is 132. And if I stick that on my calculator, I get approximately 0.045. So if you pull from this box of bulbs, two of the bulbs, the chance that both will fail is 0.045, right? Or 4.5%. B says, find the probability that both light bulbs pass the test. Okay, so in this case, right, we're looking for the probability of B1 and B2. So that's going to be their dependent event. So it's the probability of B1, right, times the probability of B2 given that B1 occurred. That's just our way of doing that. Okay, so we know we're going to multiply two fractions here. I know for the first pull that I'm pulling from 12 bulbs. Okay, and how many of those bulbs pass? 9. For the second pull, we've already pulled one of the 12 bulbs, so we only have 11 bulbs to choose from. Okay, if I want the second bulb to pass, I know there's 9 total, but I have to take one out for the first one, right? That passes. So I have 8 to choose from. 9 times 8 is 72 over the 12 times 11, which is 132. There's approximately a 0.545 chance that all will pass, right? Or a 54.5% chance, right? Can I go to C? C says, find the probability the first light bulb fails the test and the second light bulb passes the test. So I'm going to find here the probability of A1, right? The first bulb fails, and B2, right? The second bulb passes. So this is going to be the probability of A occurring, right? Times the probability of B occurring given A. Okay, two fractions. So the first pull, I have 12 bulbs to pull from. The second one, I have 11. Can I just do the totals right away? Okay, and then if I'm looking for the first bulb to fail, how many of the bulbs fail? 3. Okay, and then for the second one, right, it's going to be out of 11. But how many of the bulbs fail given that the first one, I'm sorry, how many of the bulbs pass given that the first one fails? It's 9. We don't have to take any away because the first one failed, right? So 3 times 9 is 27. 12 times 11 is 132, which when you stick that on your calculator is 0.205. So there's a 20.5% chance, right, that the first one will fail and the second one will pass. Are we okay with that? Then the last one says, find the probability that at least one light bulb failed the test. See, at least one, right? So I'm going to go over here, find the probability of at least one fail. Let me do this. Isn't that the probability, 1 minus the probability of not at least one fail? So that's the same as 1 minus the probability that I could say all pass? Or could I also say the probability that none fail? Is that the same thing? Wait, didn't we find the probability that all pass? Wasn't this one up here? Part B? Isn't this the probability that all pass? So I'm going to highlight that in green, and then I'm going to bring, right, which was this 0.545. So I can then stick that, right, in that location there, right, because it's the probability that all pass. So this is going to be equal to 1 minus the probability, right, 0.545, which when you do that is 0.455. Or a 45.5% chance that all pass. Okay. Are we good with that? Last one. We can use the multiplication rule in reverse to determine whether or not two events are independent. So if events A and B, right, are independent, that only occurs if and only if the probability of A and B is equal to the probability of A times the probability of B. So 4 says, of the works of art at a large gallery, 59% are paintings and 83% are for sale. When a work of art is selected at random, let the event that it is a painting be A and the event that it is for sale be B. So let's just write that out here so we have it down below. So A will be equal to a painting, and B is that it's for sale. So it says, what are the values of the following probabilities? The probability of A and the probability of B. Well, they tell you in the problem that the probability of it being a painting is 59%, 0.59, right? Because we have that right here. 59% are paintings. And the probability of B, they tell you right up here that it's 83% are for sale, right? So that's what's going to go here. And that's going to be equal to the 0.83. And we have that. It says, suppose you're told in part B, right, that the probability of A and B is 0.51. Are the events independent? Explain. So we know, right, from up above that the probability, right here, of A and B is equal to the probability of A times the probability of B. Okay, and we could fill in, right, the probability of A and the probability of B here. Notice I put the question mark above that to say, are they equal? And so we know that this is 0.59 times this is 0.83. So, but they tell us in the problem that the probability of A and B is this 0.51. So obviously on the left side, you just bring down the 0.51. How about 0.59 times 0.83? Well, when you multiply those, you get 0.490. Is that a true statement? No, it's a false statement. Those aren't equal values. So therefore, is it independent? No, it's not independent. Get the idea? Okay, and then for 5, it says when a child is brought to a pediatric dentist for a checkup, the probability that she will have cavities is 0.35. The probability that she will have dental insurance is 0.62, and the probability that the child will not have cavities nor be covered by dental insurance is 0.19. Let the event that a child has cavities be C, and the event that a child has dental insurance be D. Okay, so I will write that here. C is cavities, right? And let's let D be equal to has dental insurance. Okay, it says, what are the values of the following probabilities? Uh-oh. Do they tell you what the probability is that that the child has cavities in the problem? Sure does. It says the probability that she has cavities is 0.35, right? 35%. Do they tell you the probability that they have dental insurance is in the problem? Yep, that's the next part of the sentence, right? The next phrase is the probability that he or she has dental insurance is 0.62. The probability of C and D, do they tell you the probability that the child has dental insurance and has a cavity? The probability the child will not have cavities, nor, they didn't quite give us all that information. They didn't tell us C and D, did they? Okay, so we're going to have to make a chart then in order to do this. Let's see here. I like making 1,000 two-way tables, so I'll do that. So I'll put has cavities here. No cavities. And then total. Here's going to be dental insurance. And then here is no dental insurance. And then total. So I'm going to use a 1,000 two-way table. So we know that the probability she has cavity is the 0.35. So has cavities, right? That's going to be the has cavity total here, right? and that's 0.35. So 0.35 of 1,000 is 350, which then tells me that this is 650, right? Because they have to add to be 1,000. But then they tell you that the probability she has dental insurance is 0.62. So that's going to be this section right here, isn't it? 0.62 of 1,000 is 620. And if that's 620, then we know this is 380. So we're doing really good here. Okay, and then the last one is the probability that the child will not have cavities nor dental insurance is 0.19. Well, isn't that this cell right here? No dental insurance, no cavities. And if it's 0.19, that's 100 and then 90 goes there. Well, then I can fill in my other numbers. I know that 190 and 190 adds to B, right, the 380. And then I could go across this way to come up with these two. So 350 minus 190, this has to be 160. And then 650 minus 190 is 460. So doesn't the probability of C and D, dental insurance and cavities, have to be this cell right here, the 160 thousands, right, which is the 0.16. Okay, are we okay with that? So the last question is, are C and D independent events? So if C and D are independent events, that means the probability of C and D, right? Whoops. We're going to look to see if that equal to the probability of C times the probability of D. Well, we know from up above, right? They set us up here answering these to get those values. So I can do the 0.16, is that equal to the 0.35 times the 0.62? So 0.16, is that equal to 0.35 times 0.62 is 0.217. Is that a true statement? The answer is no, it's false. So therefore, it's not independent. Okay, and you can see there's a summary there at the end. You guys can take a look over that. And with that, that will wrap up the lesson.